Hi, welcome to a brief history of Unicode by Alex Blewett. For those of you who don't know me, I've been around the Eclipse world for a while, but this is going back even further than time with that. So to start off with, what is Unicode? Unicode's an industry standard for being able to represent text that came around about just before the turn of the millennium. It defines a number of different code points that map to characters, but not all code points or characters are visible. Sometimes you have control characters that are inside there. Not all characters are actually representable themselves as a standalone thing. They might be accents that amend or modify an existing letter. And not all code points are defined. So you have some undefined code points as well. But it does include all of the major idea graphs from a variety of different languages, both current and in the past as well. So, for example, the Unicode code point in hex 41 corresponds to the capital letter A, and the Unicode code point 20AC corresponds to the euro symbol. So, quick pop quiz then. What size are Unicode code points? Are they 8-bit, 16-bit, or 32-bit? Yes, that's right. It's a 21-bit code point. They're 21 bits wide, which isn't a great format for storing data in computers. But you might ask yourself, how do we end up with 21? That doesn't kind of make sense. But to explain that, we have to look backwards in time. Character sets from the past were originally based on a single byte. So things like ISO 8859-1 or code page 1252 from a Windows variety, different flavors of that like -2, -9, ASCII, EBCDIC, and multi-byte characters like 2202CN, 2202JP, and 2202KR. But what do all of those things actually mean and do? Well, what you have to do when you have a character set is decide what number corresponds with what letter. So we can define hex value 41 to be A. But then what does D0 mean? Well, it can either be a capital F if you're in an ISO 8859-1 code. It's undefined if you're in -3. And then in 8859-9, it's a capital Y, which is a Turkish soft G sound. And then finally, there's EBCDIC, which doesn't agree with anything, which says that this is a closed curly brace. And the thing is, all of the ISO standards for character sets really base themselves on top of ASCII. Well, apart from EBCDIC, we'll talk about that later. So let's look into ASCII. What size are ASCII code points, 8, 16, or 32 bits? Well, hopefully everyone knows this, that ASCII is a 7-bit code point. It stands for the American Standard for Code for Information Interchange, and it was designed to harmonize incompatible encodings that were around at the turn of the century when telegraphs started to be used, and evolved from that code point from there. ASCII was really the Unicode of the telegraph era, and the first 128 characters of ASCII are included as a subset in Unicode, in ISO 8859-1 or Latin 1 or code page 1252 on Windows. But to understand Unicode, we have to really look back at ASCII and find out what it is and where it came from. Well, it can sort of help if you look at the ASCII code chart, which defines a bunch of different fields inside here. This is showing down on the left-hand side is the lower nibble, and then across you've got the high 3 points in the ASCII code set. We've got different elements inside there, the upper and lowercase letters on the right-hand side. And one of the nice properties of ASCII is that there's a bit that's set depending on whether it's uppercase or lowercase. So there's a very quick test if you're looking to see if it's an uppercase letter, you can just look at that bit. We've then got the numbers, which are shown in the right here, 0 through 9. But the nice feature about the numbers is that the lower nibble is actually the same value as that number in hex. And so if you want to find out something's a number, you can just look at the top 3 bits. If it's 0, 1, 1, then it falls into this number category. And you can actually then just take the lower nibble of that value to get the numerical value. There's then punctuation symbols inside there and control characters inside. Those control characters are ones that have existed since the telegraph era. So we've got things like being able to ring a bell, being able to put a new form feed for new things. There's start of text and end of text characters and so on. But where this still applies today, you might notice that we've got control characters that we use on a regular basis. For example, Control M maps to carriage return, and Control I maps to horizontal tab, and Control G maps to bell. And in fact, the control bit is then the top bit inside the sequence. So you can have things like Control W, Control R, and so on, and they all map to the corresponding controls inside there. Now, many of these control characters are obsolete, but they stem from telegraph and teleprinter days. And some of these characters are allowed in XML, but the majority of them aren't. So XML allows you to have carriage return, line feed, and horizontal tab within text, but it doesn't allow any of the other ASCII control characters inside there. Mainly that's because they were used for printer mechanisms. So horizontal and vertical tab allowed you to move the carriage the printer unit, the printer element that moves across the page, to be able to move sideways or downwards. And then we had line feed, which rotated the drum, and form feed, which then rotated until the next page, or in the case of laser printers, it finishes the page and prints it out. And we still use that today. Control L will clear the terminal screen, because that's effectively what a new page was at the time. And some are used for notification. So the bell is used for ringing the bell at the other end for teletypes. But when you're dealing with computers, that will flash the screen or make a beep sound as you go through things. And then there's some that were used for interacting on telegraph, which really aren't used these days. There's acknowledge, negative acknowledge, start or end of text. Escape, of course, we use today if you use Vim. There's synchronize, there's null, and so on. The most common one that you're likely to come across accidentally today in the Unicode sequence is when you do Control Q or Control S, which is pause input and then resume input. And you might find that when you do that, sometimes your screen appears to hang, but what you've actually done is sent a control signal to the terminal to tell it that you want it to stop doing everything or then start doing things again. Now, telegraphs and teletypes revolutionized communication across long distances, because you can actually transmit sequences via an electric cable to a remote end, which could then be decoded. Now, in order for data to be transmitted across such a connection, you had to agree what the encoding of that information was, and it needed standardization. And we actually had ticker tape and ticker tape printers that were used to be able to transmit or store this information to be able to print them out again. And one of the things that was used in ticker tapes was punched holes. And the reason why punched holes were used is because you could then read them optically quite quickly. And in fact, this still hangs around today, because we've got dev TTY in Unix, which is a teletype device, and you've got dev TTY S1, which is the teletype on serial 1. If you've ever got a console or a Raspberry Pi, you'll have seen some of those things being printed. And teletypes, telegraph paper and optical reading were used in some of the earliest computers. This is a photograph of the reconstruction of a Colossus computer, which was used to crack codes during the war. And where the arrow is pointing, there's actually a stream of paper tape which has got a message encoded on it that's then being read optically and then processed with the valves that are running inside that computer. So how do you encode data onto that tape? Well, it turns out that there was a standard that grew out from Bordeaux Murray and turned into ITA1 and ITA2. Bordeaux created the first fixed length 5-bit encoding and also gave his name to baud as a rate of symbols per second, not bits per second. And ultimately, the Bordeaux encoding became known as the ITA1, International Telephone Alphabet 1. And that was created in about 1870. So we're going quite far back. From that evolved the Murray encoding in about the 1900s, which introduced null as 0, which we still use today, and introduced some of the characters like backspace, carriage return, and line feed. And that ultimately evolved to ITA2, which is the one that was the last version of the coding that was used before ASCII was invented. Here's what the ITA2 alphabet looks like. So there's 5 bits inside there. There's a section of small holes down the middle, which are sprocket holes, and each of those letters is encoded with a sequence of bits on there. So this is how you would do hello world in telegraph code. Now, the astute of you will have noticed that 5 bits isn't enough to be able to represent all of the characters and numbers in the English language. So in fact, what happened was that there was a concept of shifting. And the shift is like a typewriter shift. It allows you to move to a different layer inside there. And it meant that decoding was based on state. So if you were reading something in letter mode, you might have hello world. But if you were in figures mode, then you'd end up with something that was just complete gibberish. Now, both of these codes borrowed from another short code invention called Morse Code. And Morse Code is an example of a variable length encoding rather than a fixed length encoding. Morse code was really designed to be able to either send radio or light signals across long distances without there being any cable between them. And it used dots and dashes, either with a short beep or a long beep, combinations of those to be able to represent characters. It was also a form of doing Huffman encoding where the common symbols were shortest. So things like dot for E was used in order to have shorter encoding sequences, whereas some of the longer ones like Z and L have 4 dots or dashes inside them. And this goes back to about 1840. And it's practical for humans to be able to decode and send by ear. And so if you wanted hello world in Morse code, then it would look something a little bit like this. Most of the characters that you use in Morse code are 4 characters long. There are 5 when you come to digits if you need to send them, but the common ones that you'll use, like E in this case, or I or O, generally tend to be the shorter ones of those things. Now, dots and dashes are all very useful, but how does that fit in with computers? Well, if we think back to tapes, that's quite good for having a short sequence of things going forwards. But if you want to encode more data, then you need more space. And that's where punch cards came from. Punch cards were used in the mainframe days in the very early era of computing, where you had an evolution of tape, but not as a continuous stream, but rather as discrete units or discrete lines. And punch cards were created by Herman Hollerith, who went on to found IBM, and originally created for a US Census card. And punch cards worked by having a sized amount of card with vertical punches marked inside them. And still, in some places in America, hole punches are used today to record voting systems. The reason why punch cards were quite useful is if you are tabulating data, you can perform a radix sort to be able to bring them individually into different groups. And that was quite useful for when sorting out responses for a number of different, say, candidates that you were voting for in an election. So here's what a punch card looks like. And this is just a Fortran statement, which has got some symbols inside. What you might notice down here is that we've got the numbers 0 through 9. So you could encode a sequence of numbers on there. And there's also some that exist above the line as well. And those above the line ones, combinations, were used to be able to represent letters, which is the extended form of the card punch. And punch cards were created that size because Herman Hollerith had a bunch of machines for counting money, and the silver dollar size of the bank card was about that size. So actually, it was quite easy to be able to promote reuse of existing mechanical mechanisms to be able to fit in with this size. So when do you think punch cards and punch details were first used? Well, it turns out that they go quite a long way back to the Jacquard loom in the 1800s and then the US Census in 1890. And these punch cards could be used to drive a mechanical system for being able to roll and do some kind of processing. And from a musical perspective, even be able to play a musical instrument, either in the form of a piano or in form of an electric organ. So punch cards have really been with us for a good couple of 100 years and used for over 100 years in terms of being able to do computing or taking action processing. But having said that, we've still got a certain amount of legacy with punch cards today. The cards were 80 columns wide. That's kind of what fitted at the time within the space. But that led to the early terminals, like the VT100, 220, and 320s, as being 80 column systems because it fitted in with being able to display a whole line that was encoded on a punched card. And some IDEs and text editors still have that wrap set up by default. But you also find for some messages that they tend to want to wrap at 72 characters. And one of the reasons for that is that in the original Fortran cards, you used to be able to encode the line numbers or comment in columns 73 to 80. And so it didn't actually matter what you would have inside there because that was the size that you would have messages in. But even today, we still find that git commit messages are wrapped at 72 characters. Now, why would you want to have something in there when you could have an extra 8 characters worth of data? Well, when you have a program, it looked something like this. Each one of these cards represented a line, and if you accidentally dropped them, then it would be a big problem in there. So as you were typing out a line and punching the holes in as you go, you could then encode a line number on it. And that lasted into languages like BASIC, where you had 10 print hello world, 20 go to 10. The same sort of thing happened on these punch cards as well. But by putting the line numbers in 73 to 80, you could then use one of these sorting machines. So if you did accidentally drop a whole bunch of stuff on the floor, you could use that radix sort machine to be able to put them back in. Of course, developers being lazy implemented their own mechanism, which was just to draw a diagonal line across the cards, and then you could visually compare if that line lined up as you had expected. But all of these cards were encoded in something called EBCDIC, and EBCDIC is an extended form of binary coded decimal. Binary coded decimal was a big thing back in the 1970s, and it was a way of using the lower 4 bits of binary to be able to represent digital values. So 0x11 would be decimal 11 in binary coded decimal. And in fact, early processors that came out, like the 6502, which was in the original Apple, and some of the home computer machines had binary coded decimal instructions put in. You could put the processor into a BCD mode using SED, and then you could put it back to normal arithmetic mode by using CLD. And that would then allow you to do additions in binary coded form. And so that led to EBCDIC, which is the one that's used in mainframes because it's the extended BCD interchange code. And so on our EBCDIC card, we've got the numbers 0 through 9. They're represented just as a single element inside each of the rows, and you can see the 0 through 9 inside there. Letters were then a combination of those. So we went through 1 through 9 on the numeric values, and then we had, if you like, a top shift bit and a lower shift bit, and then the 0 shift bit as well. And so if you had pairs of those, that would form those letters, and then the special characters were encoded at the end. But one of the properties of EBCDIC that most people hate is that it means you don't have contiguous letters within the code page table itself. And so here's an EBCDIC equivalent version of the ASCII code that we already looked at in terms of being able to see where they are. And you can see that the characters aren't lined up. There's no sense to it. They're all just properties of how the physical realization of the card evolved rather than being designed for any particular sensible values. To be honest, though, you probably haven't seen EBCDIC before. It only really exists in IBM mainframes, and even these days on IBM mainframes, they can support Unicode just fine as well. But there are subtle properties of that. So the sorting orders aren't right. If you're using a C shortcut to find out if something's lowercase, you can't use the bit masking as you could with ASCII, and you can't use the, if it's less than A or greater than Z kind of mechanisms to be able to set these things up. But what's interesting is EBCDIC was created about the same time as ASCII was. They both derive from the 1960s or thereabouts. But the reason why IBM went for that is because their mainframes had the peripherals and they had the mechanisms and they had the readers already in place. And so it was the cheap way of being able to reuse legacy technology in their new build infrastructure. And of course, that happens quite a lot today with some of our new things. So putting everything together, you've got a path that looks something like this. On the physical side, you've got automation with the Jacquard loom in the 1800s, leading on to the Hollerith card and ultimately Fortran to get into the sequence. Whereas on the radio and telegraph side, you've got Morse code, which leads to Bordeaux code, which leads to the Murray ITA2. And then together, combinations of what came out with Fortran and what came out with ITA2 led to this development of the American International Interchange code page. That then led to the ISO 8859 things, which were then single bits inside, but that went on to lead the development of Unicode 1 back in 1991. And to put things in perspective, in 1991, there wasn't the internet, there wasn't Google, there wasn't Wikipedia. It was, there wasn't even there was a kind of international network, but it wasn't really what would become the internet or HTTP for quite some time. And even in Unicode 2, which came out in 1996, Java had only just been released by that point. It was about 1 year old. And it was actually quite a ballsy move at the time to base Java on Unicode, given how fresh it was. But looking in hindsight, seems to have been the right decision. But why did Unicode go from a 16-bit, which everyone could understand, to a 21-bit code page? Its problem was that 16 bits weren't enough to represent everything. And so to extend this, they had the concept of additional planes that were added on the top. And plane 0 was the basic multilingual plane, which was the 1.x series. Plane 1 is the supplemental multilingual plane, which then added emojis, Egyptian hieroglyphs, other graphics characters, and various demos. And then from 2 to 16, there were various other supplementary planes that you'd want to be able to use in there. But it doesn't really explain why we've ended up with a 21-bit encoding. And the thing is, to represent additional planes requires additional encoding. So you might wonder why they bothered going up to 16, why not stop at 15, or why even not stop just at 4? Well, the reason why it's 21-bit is because there's two different ways of encoding Unicode when it's transferred from one place to another. UTF-8, which uses bytes or octets to be able to represent content, and UTF-16, which uses octet pairs or 16 bits or words to be able to represent content. And the Unicode transformation format says how to encode a point. So while the logical code for the euro symbol is 20AC, that can be spat out in two different ways. You can either write out the low part first or the high part afterwards. And that's because UTF-16 can either be big endian or little endian, which is a term that comes from Gulliver's Travels when people are talking about which side of a boiled egg to start eating. To solve this for UTF-16, you can write out a byte order mark, and the byte order mark is FEFF, which is written out in the front. And depending on which order that's written out, you can then know how to interpret the rest of the file that comes up. What you might see sometimes is you might see a thorn and then a Y with an diaresis on the top, which is how it would look if it was shown in a standard text editor, ASCII editor that didn't understand Unicode, and which order that in might indicate something. but it's still only 16-bit. How do you represent the other planes that are going to be encoded inside there? The way that they did that was they carved out a space within Unicode 1 to represent surrogate pairs. And a surrogate pair is a high pair and a low pair that represents the additional plane data inside there. And that gives us 10 bits in the high pair and 10 bits in the low pair. But of course, 10 out of 10 is not 21. But the reason it's not 21 is that you don't need to encode a plane 0, the plane 0 basic multilingual plane, because that's just everything else inside there. It's just that within the BMP, we carve away a certain amount of data to be able to store these surrogate pairs, and those surrogate pairs themselves can then add the other 16 bits inside there, which means in total you end up with 21 bits. So consider the 430 symbol, which it is about now. The Unicode symbol for the 430 is 1F55F, so it's actually in plane 1. And plane 1 is encoded as 4 zeros. You've then got the two other parts in there, the FF and 5F, to be able to represent those things. And if you put it together in UTF-16, then the highlighted gold parts on here are the high and low pairs that are indicated. And so the high and low pairs are then written out in that form, and you can decode and put it back in as it's shown. UTF-8, on the other hand, stores its data in octets. And rather than having a fixed number of things that needs to fit in, it will go into a multiple individual octets instead. So anything that's ASCII and less than 127 goes in one octet. Anything that's above that but below 0007FF will go into 2 octets. And some of the longer ones, including emojis, will then go into 4 octets. Now, the way that's encoded is when you have a single octet, they always start with a 0 bit, and therefore you can encode everything in ASCII in exactly the same way in UTF-8. Multiple octets always start with 1, 1, and then continuation octets start with a 1, 0. And this is something that a couple of people that you might have heard of, Ken Thompson and Rob Pike, created as part of the discussions on Unicode for being able to say how they were. So what does some of this look like then? Well, we talked about our A value before. That's just written out as a single bit. But if you've got the clock symbol, then the plane 1 is 00001. F5 and 5F we've seen before in their bit patterns. And so that's going to be encoded as 4 octets. Now, the first octet begins with 1, 1. That indicates that there's more than one bit inside there. And then the remaining ones are 1, 0, 1, 0, 1, 0. And you'll keep reading through those until you see the number of bits, the number of elements that you expect. And the next one is then going to begin with 0 if it's a single octet, or 1, 1 if it's a multi-byte octet. The nice trick is that the number of bits in the first part tell you how many bytes to expect afterwards. So in this case, because we've got 4 1s inside here, then you know that there's 4 bytes in total that make up the symbols. And this makes UTF-8 easy to understand, because if you jump in the middle of a sequence of things, you can actually scan backwards or forwards until the start of the next character, which isn't always the case in some things. Now, you might see something being encoded in UTF-8 as a UTF-16 byte order mark. Doesn't really make any sense at all, and it's only generated by Windows. And even now, it's been a long time since I've seen this spat out as part of editors. So given that this is an international conference, I thought it might be interesting to see how the flags of all nations are encoded inside there. How do you encode flags without necessarily encoding a whole lot of character points inside that might change over time? Well, there's regional indicator symbols between A and Z. And if you put pairs of them together, then they will be translated into the flag using font ligatures that you might have inside your system. So font ligatures are when you type in FF or FFI together and they join into one glyph on your screen. And so actually this is a rendering presentation in the tool that you're using. If you put G and B next to each other, you'll end up with the UK flag. If you put E and U next to each other, you'll end up with the European flag, and so on. So we've arrived at Unicode as being a 21-bit code point that evolved to 21 bits from 16 bits with encodings as a way of being able to store multiple bytes inside there, and is self-synchronizing. And for UTF-16, we use surrogate pairs as the high and the low values inside there. And all of this has been evolving over the last 200 years, and that brings me up to time. Thank you very much.
So I'm happy to answer any questions that you might have. I've seen we've had a couple of them being posted in the chat today. One of them was, will we still be able to read Unicode documents in 1,000 years' time? Well, I don't think I'm that good at predicting into the future, but one of the things that I would say is that there's been a remarkable amount of consistency in being able to read old documents, whether that's in EBCDIC or ASCII or some of the other character sets. So I think Unicode certainly stands the test of time. I think what will perhaps be interesting is the meanings of some of the hieroglyphs and the emojis that we use today, because there are some emojis that have taken on additional meanings in popular culture rather than the actual name of the vegetable that they're referring to. And I think that might be interesting because some of those meanings I think will be lost over time, but there will certainly be a way of being able to decode what those symbols are. But in the same way that we need to have a Rosetta Stone for understanding what the Egyptian hieroglyphs are, we might need to have some similar kind of mechanism to be able to explain what we mean by some of those emojis that come in. So from understanding what code point it corresponds to, yes, understanding the meaning of some of those messages, I think that might be a little bit more challenging. There was another question about, given that Unicode means that you can't just read in with bytes and be able to do processing on a byte level, does that mean that you need to have some kind of specialized library to be able to use text? Well, realistically, I'd recommend if you're doing any kind of Unicode text processing, then you look at the ICU libraries. So there's an ICU for J, there's an ICU for C and C++, and those are the common ones that are used for dealing with Unicode text characters. Because as we were just talking about with the flags, if you have GB as the symbol for the UK flag, and then you just do something as simple as a reverse string, then you might end up with BG, for example. Or if, depending on how the bytes are encoded, you might end up with a complete different mix on that. And we didn't have time to talk about some of the customizations that you've got on emoji symbols with the zero width joiner and being able to combine together certain symbols like a man and a plane to represent the pilot. That's how it is represented under the covers, or indeed some of the skin colors where you have a smiley face, but then you can tone it with a skin color inside there. Another question that's common is emojis in log files. I think we're seeing, particularly with shells, a number of innovative uses of emojis to highlight and draw attention to particular lines, maybe using an exclamation mark symbol for a warning or a red cross to be an error one. That can certainly be useful when you're looking at it within a console. In a log file, perhaps those escape sequences don't come out as obvious as you would like, but there's ways of being able to present that, and certainly some of the web-based viewers of log files are able to render either the ANSI escape sequences, which are what are used to change colors, or to be able to represent those as well. I'd argue the emojis are probably slightly more understandable when you look at a log file than some of the ANSI escape code sequences with the tilde square brackets for being able to shift into different modes. So that might be something that's interesting for some people. And then a final question there, which organization is in charge of defining the symbols in Unicode? Well, there's a Unicode consortium who actually look for what the definitions of those symbols are and what the code points are that they're using. But there are specific subgroups underneath there that are looking at different aspects of it. And probably the one that has seen the most growth over the last couple of years has been the one that's been extending new emojis into that. And there are proposals from both phone vendors and operating system vendors and other interested parties for suggesting new emoji icons to be added into Unicode itself. But then there were other aspects of Unicode that we didn't cover, like the ability for being able to represent Egyptian hieroglyphs, for example, or some of the other languages or some of the other standards. And languages, and particularly some of the character sets in the pictograph forms, are we're discovering and adding new characters in all the time. And so Unicode is growing over time, but it's the Unicode consortium that will be able to decide if there's any new characters that come on board. And then last answer to question, will this presentation be available? Yes, I will be updating it to SpeakerDeck. I haven't done that at the moment, but I shall do so within the next few days, certainly by the end of the weekend. So you'll be able to get that presentation off. And this presentation, I believe, is also going to be uploaded and available on YouTube afterwards on the Eclipse Foundation channel. So if there's anything that you want to go back in to be able to see information in there, you should be able to get them either from the SpeakerDeck presentation or from the Unicode stream. And if you want to tweet me, then I'm at @alblue. Thanks very much for your time. Hope you enjoyed the presentation.